In this lecture, I will explain the losses in a DC machine. So, we already discussed. If you want to know the machine's performance, there are performance indices are required. The first one is efficiency, and second one is regulation. And the regulation part were over. So, if it is a generator, we should concentrate on voltage regulation. If it is a motor, we should concentrate on speed regulation. And coming to the efficiency, you have to calculate the losses. Suppose if you take a person, he has its own drawbacks. Suppose in one classroom 60 students are there. 60 students are not passed in a particular subject. If they are passed, it's very good and very nice also. Some of the students are failed, we can treat that it is a losses. In an ideal case, 100% pass percentage will come. But coming to the practical cases, some failures will be there and loss is also there. We can treat them as a loss. Similarly, same way, coming to our machine also, machine consists of losses. If we know the losses, we can find the efficiency. And what are the losses are there in a losses in a DC machine? Losses in a DC machine. The first loss is called copper loss, and second one is magnetic loss, magnetic loss, and third one is mechanical losses. These are the losses are present in our DC machine. So if you go for the DC generator, if you go for a DC generator, how many windings we have? One is an armature winding and another one is shunt field winding. If it is a generator or motor, we have a two windings. If it is go for the DC series motor, the field winding is connected in series with the armature, and the current which is flowing through this one is IA. Okay, here also we are having two windings. So if it is a generator, the current direction is upwards. If it is a motor, the current direction is downwards. So the first one is IA square RA. This IA square RA is called the armature copper loss. Armature copper loss. And next one is ISC square into RSC. This is called series field copper loss. Series field copper loss. And one more loss is also there, that is ISH square into RSH. ISH square into RSH. This is shunt field copper loss. The loss which is taken place in the copper winding, that is, winding is made up of copper. That's why it is called the armature copper loss or series field copper loss or shunt field copper losses. So that's why the name is assigned as a copper loss. If you go for the magnetic loss, means iron, and so this is also called as a iron losses. So these are all two types. Iron loss or core loss also. The first one is hysteresis loss. Hysteresis loss. And second is eddy current losses. So eddy current losses. The hysteresis loss formula B max power X FV, that is neta, and eddy current losses is equal to K into B max square EF square T square. And third is mechanical losses. So friction loss and windage loss. If you take any machine, the losses can be classified as the major classification only one thing, that is variable losses and constant losses. Variable losses and constant losses. See, coming to the copper loss, Ia square Ra, if you take a DC shunt motor or DC shunt generator, I don't have this ISC square RSC, the series field copper loss is 0. As load is variable, Ia is also variable. Yes or no? This we can trade as the variable loss. This I can be treated as the variable loss. If I am going for the DC series motor or generator, this is series field copper loss. Ia is variable. Ia is equal to IL is equal to ISC for DC series motor or DC series generator. So this is also called as the variable loss. And coming to the shunt field copper losses, the same terminal voltage will be applied across the shunt field winding, and terminal voltage or supply voltage will be applied. So if it is a generator, it is a terminal voltage, and same terminal voltage or supply voltage will be applied across the shunt field winding. Then RSH is also constant, then ISH is constant. This I can be treated as the constant loss. This I can be treated as the constant loss. So this hysteresis losses and eddy current losses is also constant. It does not depends on the current. So does not depends on current. So these are also constant. Why? Because this Bmax is a maximum flux density is constant. F is a constant. The frequency which is generated in the armature, okay, either it is a DC, but the waveform which is induced in a DC, yes, it is a flat top, right? So coming to the eddy current losses, eddy current loss is equal to K into B max square F square T square, and in this also it does not depends on IA, and this also we can treat as the constant loss, comes under the category of constant loss. And friction and windage losses, so initially to overcome the friction some power is required, that loss is called the friction loss. So once it will be rotated, the wind will be opposes the speed of the motor or speed of the generator, then windage loss will be produced. So that is comes under the category of mechanical losses, and this is also constant. It's also constant. Now we are segregating the losses like this. So magnetic loss plus mechanical losses, magnetic loss plus mechanical losses is equal to stray losses. So magnetic loss plus mechanical losses is equal to stray losses. Stray loss plus shunt field copper loss. Shunt field copper loss is equal to constant loss. Now the constant loss is, it is a addition of stray loss plus shunt field copper loss. Stray loss plus shunt field copper losses. And now variable losses is equal to, so variable losses is equal to armature copper loss plus IAC square into RSC. IAC square into RSC. So IA square RA plus IA square into RSC. IA square into RA plus RSC. RA plus RSC. Okay. Here you can observe that, so in a long shunt and short shunt, okay, small current will be different, and you can remember IA square RA plus IAC square into RSC. For a DC shunt motor or shunt generator, this part will be 0. This part will be 0. DC shunt motor, DC shunt motor, this part will be 0. Okay. And what DC series motor, and both are present. What is a power flow diagram of a DC generator? Power flow diagram. So power flow diagram of DC generator. So generator EEG is equal to Vt plus Ia into Ra. Eg into Ia is equal to Vt into Ia plus Ia square times of Ra. Ia square times of Ra. So if I am the input to the generator, the input to the generator is mechanical power. So mechanical power input. So output of driving machine. Yes, this we can treat as the output of driving machine. So that is given to electrical power developed. This is electrical power developed in the armature. So that is Eg into Ia. Eg into Ia. From this, okay, you can subtract copper losses. Then I will get electrical power output. This V into Ia. This is power output. So from this mechanical power, if we subtract the iron and friction losses, that is called the stray losses, then I am getting this the power which is developed in the armature. So from this equation, Vt into Ia is equal to Eg Ia minus Ia square into Ra. So then I got the electrical power output. This is called the electrical power output. The electrical power output. Suppose if you want to draw the power flow diagram of DC motor, power flow diagram of DC motor, the DC motor voltage equation is V equal to EV plus Ia into Ra. If you multiplied Ia, so V into Ia, EB into Ia plus Ia square into Ra. So EB into Ia is equal to VIA minus Ia square into Ra. This power is called the mechanical power which is developed in V into Ia minus Ia square Ra. So the input is electrical power input, that is V into Ia. From this we are subtracting Ia square Ra, that is called the copper losses. Then I am getting the gross mechanical power output. So gross mechanical power output, that is EB into Ia. From this power, if we subtract iron and mechanical losses, then I got the motor output in watts. This is called the power output. So observe these two power flow diagrams. It should follow in a reverse manner. Check that this power output is input for this one, and electrical power output is electrical power input. After that we subtract the copper losses, then I am getting the gross mechanical power, and after that I am subtracting the iron and friction losses, then I got it the power output. And see here, so this is a power. If you follow the power flow diagram in a reverse manner for a generator, then I got the motor diagram. And the next one is efficiencies of DC machine. The first one is mechanical efficiency. So mechanical efficiency is equal to the output power is in electrical power divided by input is mechanical, right? Yes or no? Multiplied with 100. So Eg into Ia divided by output of driving machine multiplied with 100. So if you observe here, this is the input is output of driving machine, and the output of this box is electrical power developed. So this is for generator. This mechanical efficiency is for generator. So coming to the electrical efficiency neta E is equal to, so if you observe the electrical output divided by Eg into Ia, so Vt into IL divided by Eg into Ia into 100. If you go for the overall efficiency percentage efficiency is equal to output power divided by input power multiplied with 100. The output power is Vt into IL divided by input power is Pin into 100. So coming to the percentage efficiency of generator. So output power divided by, we know the electrical terms. The electrical terms are output for the generator, output power plus losses into 100. If you go for the percentage efficiency of motor, input power minus losses divided by input power into 100. We know the electrical term, that is input power. So input power is equal to output power plus losses. Whatever the input power is there to meet our requirement, that is our output power, and also some losses will be produced. And the next one is condition for maximum efficiency. So always you observe that variable losses is equal to constant loss. So power output for a generator is Vt into IL, and the copper loss is Ia square into Ra. So we can write it as Vi, and this is I square into Ra, and Ia is equal to I. So neglecting shunt field current because it is a constant shunt field current. So percentage efficiency is equal to output power divided by output power plus Ia square Ra plus constant losses multiplied with 100. So then I got it as Vi is taken as the common on both sides and cancelled. Vi 1 plus 1 plus IRA by V, because I square RA divided by VI. I square RA divided by VI. II will be cancelled. Plus iron losses by V. So these two are cancelled now. So differentiate this equation with respect to variable. D neta by di is equal to 0. Then I will get the condition for maximum efficiency of a DC generator. So if you apply the maximum power transfer theorem, always variable is equal to constant, or load resistance is equal to source resistance. So similarly, same way I get the answer, variable loss is equal to constant losses. So differentiate this equation. So U by V method. So RA, differentiation of this one is U by V method, V into U dash minus U into V dash by V square, and V square anyway it is equal to 0 multiplied with 0. V into U dash, this derivation is 0, minus U minus at L, so that is going to right side. U into S1 into differentiation of 1 is 0, and this is RA by V, RA by V minus PI by VI square is equal to 0. VI square is equal to 0, because this is I am getting as VI, differentiation of VI. So finally I got it as IA square RA is equal to iron losses. That means variable losses is equal to constant losses. This is very very important. If you take any machine, either transformer or a DC machine or any machine, so always condition for maximum efficiency is variable loss is equal to constant losses. So with this current at maximum efficiency, current at maximum efficiency. So current at maximum efficiency, IA square RA is equal to PI. From this, IA is equal to PI divided by RA, means root of PI divided by RA. That should be equal to root of constant losses by armature resistance. Constant losses by armature resistance. If you go over the for series machines, this is for shunt machine. For a series machine, IA square into RA plus RSC is equal to iron losses, and IA is equal to root of PI divided by RA plus RSC, and this is very very important. Finally, condition for maximum efficiency is when the variable loss is equal to constant losses. So thank you guys.